Have you ever wondered what happens when a star dies? I'm not talking about a quiet fade to black. I'm talking about a spectacular, universe-shaking explosion called a supernova. And what is left behind can be one of the most extreme and mysterious objects in the entire cosmos, a neutron star. Imagine a star much more massive than our sun running out of fuel. Its core collapses under its own immense gravity. The pressure becomes so intense that protons and electrons are literally squeezed together to form neutrons. This collapse is halted by something called neutron degeneracy pressure, creating an object so dense it defies imagination. How dense are we talking? Picture taking the entire mass of our sun, a star so big you could fit over 1 million Earths inside it, and crushing it down into a sphere just 20 kilometers, or about 12 miles across. That's roughly the size of a city. A single teaspoon of neutron star material would weigh billions of tons. It's an amount of matter so concentrated that it warps the fabric of space-time around it. These objects are mind-boggling. They spin incredibly fast, some rotating hundreds of times every second, and they have magnetic fields trillions of times stronger than Earth's. But the biggest mystery of all lies deep within. What is a neutron star really made of? We know the outer crust is likely a lattice of heavy atomic nuclei and a sea of electrons. It's solid, like a crystal, but unimaginably dense. As we go deeper, the pressure increases to levels we can't replicate in any lab on Earth. The atomic nuclei start to dissolve. The crust gives way to the inner crust when neutrons begin to leak out of the nuclei, forming a solid. That's right, a fluid with zero viscosity, flowing without any friction. This neutron superfluid coexists with the remaining lattice of nuclei. It's a state of matter so bizarre, it's almost science fiction. Deeper still, we reach the outer core. Here, the nuclei have completely dissolved. We're left with a soup primarily made of neutrons, with a small fraction of protons and electrons, all in a superfluid and superconducting state. The pressure is astronomical. It's in this region that the fundamental properties of matter are pushed to their absolute limits. But the real enigma, the ultimate question mark, is the inner core. What happens when you keep crushing this neutron soup? This is where our current understanding of physics breaks down. Scientists have several competing theories, and honestly, we just don't know which one is right. One possibility is that the neutrons themselves break apart. Remember, neutrons are made of smaller particles called quarks. Maybe the immense pressure in the core is enough to liberate these quarks, creating a new state of matter called quark matter, or quark-gluon plasma. In this scenario, the core of the neutron star would be a sea of up, down, and strange quarks swimming freely. If this is true, neutron stars would actually be quark stars or hybrid stars with a quark core. Another fascinating idea is the formation of a hyperon fluid. Hyperons are exotic particles, relatives of protons and neutrons, that contain strange quarks. They are unstable under normal conditions, decaying in fractions of a second. But under the crushing pressure of a neutron star's core, they might become stable, creating a soup of neutrons, protons, and a whole zoo of different hyperions. This would soften the star's core, making it more compressible. Then there's an even more exotic possibility, a color superconductor. In the theory of quantum chromodynamics, quarks have a property called color charge. It's possible that at extreme densities and relatively low temperatures, quarks could pair up, similar to how electrons pair up in a superconductor. This would create an incredibly stable and efficient state of matter, a color superconductor. This is one of the most theoretically dense and stable forms of matter that could exist. So how can we possibly figure out what's really going on inside? We can't send a probe. It would be instantly torn apart and crushed. Our clues come from observing neutron stars from afar. By precisely measuring their mass and radius, we can constrain the possibilities. This is where gravitational waves come in. When two neutron stars spiral into each other and merge, they send out ripples in space-time. Observatories like LIGO and Virgo can detect these waves. The signal from a merger carries vital information about the star's properties. During the collision, the stars are deformed by each other's gravity. A star with a softer core, like one with hyperons or quark matter, will deform more easily than one with a stiffer core made only of neutrons. These deformations leave a specific imprint on the gravitational wave signal. By analyzing these tiny ripples, we can effectively feel what the neutron stars are made of, right up to the moment they collide. It's like cosmic seismology, using the vibrations of space-time to probe the inner structure of these dead stars. Recent observations of neutron star mergers have already started to rule out some of the most extreme theories. They suggest that the cores of neutron stars are incredibly stiff, but perhaps not stiff enough to be made purely of neutrons. This hints that some kind of exotic matter might indeed be lurking in their hearts. Every new detection of a neutron star, whether it's through radio telescopes observing pulsars or gravitational wave detectors feeling a merger, adds another piece to the puzzle. We are living in a golden age of astronomy where these once theoretical objects are becoming real, tangible subjects of study. The quest to understand the heart of a neutron star is more than just an astronomical curiosity. It's a journey into the fundamental nature of matter itself. The core of a neutron star is the ultimate high-pressure physics lab, creating conditions that we could never hope to achieve on Earth. By studying them, we are testing the limits of our theories about the strong nuclear force, the force that binds atomic nuclei together. What we learn could revolutionize our understanding of the universe. From the first moments after the Big Bang to the ultimate fate of massive stars, we are peering into a realm where the familiar rules of physics are bent and broken, and new, exotic states of matter emerge. The answer to what's inside a neutron star is still we don't know for sure, but it's one of the most exciting questions in all of science. It could be a sea of superfluid neutrons, a bizarre mix of hyperions, a soup of free quarks, or something else entirely that we haven't even imagined yet. yet. Each possibility is more mind-bending than the last. As our technology improves and we gather more data from these incredible cosmic collisions, we're getting closer to an answer. One day soon, we might finally unlock the secrets hidden in the heart of a dead star. Thanks for watching, and if you enjoyed this journey into the unknown, be sure to like and subscribe for more deep dives into the cosmos. See you next time.